In this video, I will estimate surface concentrations using a soap boat. The soap boat is a very popular at-home experiment that demonstrates effects of surface tension. Specifically, flow is generated by a surface tension gradient, which is known as Marangoni flow. In both images, a surfactant is released, causing a decrease in surface tension and a net forward movement. In general, a surfactant molecule is characterized by having a hydrophobic end and a hydrophilic end. As depicted in the image, the surfactant molecules group at the surface in order to satisfy their attraction and repulsion at both ends. This grouping is known as the surface excess concentration and can be calculated using Gibbs adsorption equation. Since the gas constant and temperature are treated as constants, the surface concentration is a function of the surface tension and the concentration of surfactant. In this experiment, I'll be using Dawn dish soap and Meyer's cleaning concentrate. The surfactants found in each of the contents list are shown below. As you can see, all surfactants are considered to be a long-chain molecule, and so I predict that the curve generated by the concentration and surface tension will follow the blue line. In these videos, I varied the concentration of dish soap by volume percent, 100% being pure dish soap. Similarly, I vary the concentration of concentrate by volume percent, 100% being pure concentrate. Using the videos I just showed, some modeling can be done to calculate surface tension. To keep things simple, we will be neglecting drag forces and assuming temperature is constant. The diagram on the left shows the soap boat with surface tension forces applied by the water in blue and the soap in orange. We can see that the forces in the horizontal direction cancel out based on symmetry. However, there is a net force in the vertical direction. Surface tension forces are described as the product of surface tension and length. At the top, surface tension forces by water are applied over the length of 3L. At the bottom, water surface tension is applied over 2L, and the remaining length L is exposed to the surface tension of soap. Therefore, the overall net force is the difference of surface tension between water and soap multiplied by length L. And finally, by Newton's second law, we can find the surface tension difference by measuring the speed of the soap boat. To measure the speed of the soap boat, I used a point tracking software and monitored the front and rear ends of the boat, and then calculated the overall speed of the midpoint displacement. From there, I plotted the speeds over time to derive the acceleration. So finally, I was able to plug in the calculated surface tension differences and plot it against the natural log concentrations of the soaps. Since manufacturers do not explicitly state the quantity of surfactants within their products, I used relative concentrations for all calculations. For example, the pure dish soap is the largest concentration of the set, and I just gave it an arbitrary value of 0.1. For dish soap, I derived a surface concentration of 1.74 times 10 to the negative 6 moles per meter squared, and for the concentrate, 5.24 times 10 to the negative 7 moles per meter squared. Both of the curves produced were quite unexpected. In particular, for the dish soap dataset, the minimum value seen after the plateau was surprising. The starting end of the plateau is known as the critical micelle concentration, in which the surfactants start forming bundles called micelles as a result of a fully occupied surface. The plateau can be explained by the high viscosity of the dish soap. I believe that the viscosity acted as a diffusion rate limiting step, or in simple terms, it took a long time for the soap molecules to dissolve into the water. The concentrate curve was maybe more surprising than the dish soap dataset. In general, it is expected that as the concentration increases, the difference in surface tension decreases. The only possible sources of error that I can think of include my method of dropping in the soap with a dropper, or maybe the locomotion of the soap boat was altered by my accidental crushing while cleaning in between experiments. This experiment could greatly be improved by two things: using a better soap dropping method, like dipping a toothpick in the soap solution and gently touching the water, also using lower concentrations, especially for viscous soaps, to reduce the diffusive rate limiting step.